In the last video, we developed a heartbeat detection mechanism, and we showed that the mechanism we developed is equivalent to a neural network with fixed parameters. So going back to the simple network we considered, this network has a single convolution layer and one linear layer. So in total, this network has two layers. Now, if we want to do more sophisticated things, it's important to have multiple layers. For an example, we can expand this neural network by having two convolution layers. So now we have convolution layer 1 here and convolution layer 2 here. And when we account the linear layers, there are 3 layers. But as you know, convolution operation is a linear operation. So it doesn't really make sense to have two back-to-back linear operations, right? If we need, we can represent these two operations as a single operation. So typically what is done is when we have multiple layers, we introduce a nonlinearity between layers. So there are many types of nonlinearities that can be used. So one of them is in fact the sigmoid function we described previously. Another common type is to use tan h as the nonlinearity, which is also called as the activation. In modern deep learning systems, we commonly used something called ReLU, rectified linear unit. So this is what the activation function ReLU looks like, right? So in ReLU, when the input is negative, the value is suppressed to be 0. When the value is positive, there is no modification done. Okay, so this is one of the commonly used activations in modern deep learning. So typically in a modern deep learning network, we have a combination of these components appearing together. So for an example, this is the system I originally had, where we had a single convolution layer and a fully connected layer. And this is the system that I just drew by introducing a second convolution layer. As a rule of thumb, nonlinearities will not be indicated separately in modern deep learning architectures. So even when there is no indications, please assume that there exists a nonlinearity. It's also possible to have multiple fully connected layers. In our application, the size of the fully connected layer, it had a input size equal to n divided by t, and the output size was 1. But in general, fully connected layers can have any input output sizes. So this allows us to use fully connected layers to reduce the dimensionality when it's necessary. So modern deep learning architectures will have combination of convolution, fully connected, and all the components that I described, normalizations, pooling, so on and so forth. So with that, let's discuss about some modern deep learning architectures. So in my example, I used a 1D signal as an example, the heart rate signal. It was a 1D signal. But in practice, we can apply the same principles to signals of any dimension. Here we are looking at grayscale images. So grayscale images are 2D signals, right? But the principles that we describe, the intuition is carried forward even in these applications. However, there is a single notable difference. In our previous application, when we were operating on a 1D signal, to perform convolutions, we used a 1D convolutional kernel. In this application, when our input is a 2D signal, we will use 2D convolutional kernels to perform convolutions. So in the diagram, the square-shaped entities you see are convolutional kernels. Now, this network, which is called LayNet, is a very old network, one of the original convolutional networks introduced in the literature. So in this network, given an input image, this was subjected to some convolution filter. The filter size is 28 by 28. Input size is 32 by 32. Filter size is 28 by 28. And in the first layer, there were 6 filters. So it's a filter bank with 6 filters. So this is layer 1. And then this was followed by a second layer, L2, which had smaller filters. So layer 1 was 28 by 28, layer 2 is 14 by 42. Again, they had 6 filters in the filter bank. And this was followed by another convolution layer, layer 3. This had filters of size 10 and there were 16 filters. This was followed by layer 4, another convolution layer. Now the filter size is 5, there were 16 filters. So this output of this layer was then subjected to 3 linear layers. Layer 5, layer 6, and layer 7. So what is different here is that in our discussion, our linear layer took a input of certain size and it reduced it to a single number. So that doesn't have to be the case all the time. Linear layer can produce an output of a different number. So for an example here, layer 5 is taking input. I don't know the size of this input, but the output is 120. So it's a linear layer that takes some input and produces 120 outputs. And then layer F6 takes input of 120 and produces an output of 84. And finally, this final output linear layer, it's taking input of 84 and producing output of 10. So in this application, the application he targeted was to do digit classification. So the output was between 0 to 9 digits, right? So there were 10 outputs in total. So the output of the final layer was of size 10. So each output in this layer was basically given the probability of obtaining a particular digit. So the first output was the probability of digit 0, second output was the probability of digit 1, so on and so forth. So the output was directly given the probabilities of digits. So in 2012, there was a network called AlexNet that revolutionized deep learning, right? So this was a breakthrough paper in 2012. So in AlexNet, a similar architecture was used, right? So given an input, again, it contained multiple convolutional layers, right? So layer 1, layer 2, layer 3, layer 4, layer 5, all convolutional layers, and then he had some fully connected layers, right? So in this particular network, they were trying to solve a problem of object recognition. So there were 1,000 object classes in this data set. Therefore, the output was of size 1,000, right? So each index of the output was basically representing the probability of a particular object. If we remind ourselves how these networks work, initially we are given a input and then this input is passed through the first convolutional layer, and as a result we will get some feature vector. So this feature vector is then passed through the second convolutional layer. We get another feature vector as a result. Then it is passed through the next convolution layer. So at each stage of this network, after every convolutional layer and after every fully connected layer, we get a intermediate feature vector. And at the end, when the input is passed through the final layer, we again get an output of dimension 1,000. So that's the output of the network. And as we discussed earlier, parameters of this network again is initialized with random values. During training, we train these parameters so that the network learns the behavior that we want it to learn. Now, when the network is learned, when the network is fully trained, what kind of characteristics do these filters capture? So if we take a step back and talk about our heart rate detection example. In that example, we initialized our filters to be heart rate signals. In other words, the filter described the kind of signal that it want to capture in the original signal. Interestingly, we can see a similar phenomenon when we train the network using machine learning. In this slide, what I've shown are the visualizations of filters of the first two layers of the AlexNet architecture. So if you look at this part, this is the visualization of first layer filters. Now, if you closely look at these filter shapes, these filter shapes are edge detectors. In other words, these kind of filters would produce a positive response when the image contains edges. So in this bottom picture, you can see what kind of image components activates the first layer filters that I have shown. So as you can see, these in fact are image components that capture edges. So the first layer of AlexNet, what it did was it was basically scanning through the image to see whether there were image components that captured edges. If there were edges, there was a positive response. And then when you look at the second layer of the network, again it was a convolutional layer. So what kind of features did the second layer filters capture? By observation, we can see that second layer captured more complex shapes. Things like corners, for example here, this filter captures a corner, then more complicated lines, then things like curves. So these were capturing more complicated shapes. Now for an example, in this image, you can see what are the types of image components that activated these second layer filters. And you can see things like corners, round shaped objects or gradients. These are the kind of image components that activated the second layer of the network. Then as we go on further and further, so layer 3 captured even more complex patterns. So we can see this pattern continuing as we go deeper into the network. So for an example, in this slide, you can see what are the types of filters layer 4 and layer 5 contained and what were the corresponding images that activated these images. So for an example here, you can see there were certain filters that were specifically activated by an image of a dog. There were certain other filters that specifically got activated when the image contained birds. Because of this property, researchers found out that intermediate layers of AlexNet network contains very useful information about what is present in the original image. Shallower layers, those are the first layer and the second layer, they contained low level information about the image. Edges, corners, things like that. And deeper layers, those are maybe layers 5, 6, 7, 8. Those layers contained higher level information that were more specific to an object type that was present in an image. This pattern was not only limited to AlexNet. Even for other networks that came after AlexNet, networks like VGG, ResNet, the same property was observed in all these networks. And as a result, features extracted from these networks were successfully used in many other downstream applications.